we've looked at the fact that power transmission is most effective using AC, so I'll just make that note briefly, or most efficient. That's great in terms of getting power from a power supply to say homes and businesses. However, a lot of the components that we, or a lot of the devices that we use actually require DC. And when we say electronic devices, we're meaning what we're really talking about there are things that, so basically sort of computers and phones, those sorts of things. Anything like a toaster or a kettle, they don't really require DC, but anything that's a little bit more advanced, so has electronics in it, computer systems, those sorts of things, then we're going to need to use DC. That means then that we've got to be able to convert from AC to DC. So I've got to be able to take an alternating current and convert it to a direct current. That process is known as rectification. And with rectification, we're going to use a component here that we're not really going to go into in any detail. I'll explain how these components known as diodes are used, but we're not really going to look at the structure of them or how the semiconductor allows the properties of a diode to be produced. What I will mention though is that they are semiconductor devices that only allow current to flow one way through them. So the symbol that we'll have a look at with a diode. The diode looks, or the symbol, circuit symbol for a diode looks like that. So the direction that current can flow through them is basically in the same direction as what this sort of looks like an arrow with this triangle. So we would call that forward biased. And with forward biased diodes, current can flow. When we're talking about forward bias, then we're basically saying that to the left here is going to be at a higher potential than to the right, so that would be a forward bias diode. If we had the diode connected the other way, so we'll keep the plus and minus at the same orientation, if we had the diode then connected in the opposite direction, that would be known as reverse biased. And for a reverse bias diode, no current flows. One last little point here as well, in order for current to flow through a forward bias diode, you'd actually need a 0.7 volt drop, 0.6 to 0.7 volts. Again, we're not going to go into that in any detail, but just to mention it there. Now, there are two types of rectifying circuits that we're going to look at. The first is known as a half wave. There's a few reasons why a half wave rectifier is used. What we'll do is have a look at circuit diagram. So we'll start out with say the primary coil of a transformer here, and then that's connected to a secondary coil. Exactly how many coils here we're not going to worry about, so whether it's step up or step down we're not going to discuss. Ultimately though, step up or step down is just going to have an effect on the way that the size of the output compared to the input. Now, just to make this simple, we're just going to have that connected to an output resistor. So what we're looking for here is the potential difference across the resistor, or the current through the resistor, in this particular circuit. So on the left hand side, we're going to start out with an input that's alternating, so we'll call this one V in. So V in would be this potential difference between these two connectors, and the input would just look like something like this. Keep in mind that if that was connected to some other circuit, then we'd have a current that would look something like that as well. So an alternating input. Now I want to just sort of step through this a little bit more carefully. So initially we're going to start with just looking at the positive half cycle. So that represents, say, this part here of the input. And so with the positive half cycle, the diode is forward biased, so current can flow through that way. It'll then flow down through the resistor and then back through the rest of the circuit. Let's put those arrows on the outside. So that's the direction that current's going to flow. So as the input potential difference increases and then decreases again, we're going to see the same thing occur with the output across the load resistor. So if we look at the output voltage, we'd see that that's going to increase and then decrease again. And then similarly, when it goes positive again later, we'd see that increase and decrease. On the flip side of that, so when we then look at the negative half cycle, so if we're considering this part of the input now, what we're going to see is something slightly different. So when it's negative there, positive there, if we come around to the diode, that means that we're going to have a reverse bias diode. So on the negative half cycle, we're not actually going to see any current flowing, and so with our output then, what we would see is that it gets clipped off, and so there's no current flowing there. I should just mention these are both time axes. And so you can see there that the output drops to 0, increases on the positive half cycle, and decreases to 0 again. Now there are some advantages and disadvantages with this circuit, so I'll just really quickly list out what some advantages are. First of all, the advantage is that only one diode is needed. Second, it achieves its purpose. The output is DC. But some of the disadvantages that we have here, the first is that even though it's a DC output, the output isn't constant. So we get that increase and decrease, first of all. And sort of tied into that, we have this issue that the output is 0 for half of the input cycle. So that means that some of the input energy that we have in the input is going to be wasted because it's not being used in the output. Now there is a way to improve that. There's an extra component in here. So to improve these some of these disadvantages, the solution to those is to use and it's not necessarily a full and complete solution, it's to use a capacitor. Now I'm not going to go into much detail here with capacitors. Subtopic 11.3 that we'll go on to next actually does incorporate a whole subtopic about capacitors, so I'll just mention here, basically a capacitor is a device that stores charge. So it goes in parallel with the resistor, and basically what it means is that on the positive half cycle, as current flows through, we're actually going to store charge on the capacitor. Then on the negative half cycle, so let me just show what that would do. So on the positive half cycle, we're going to have it going up to the top. On the negative half cycle, because the diode is then reverse biased, the capacitor takes over and starts to discharge through the resistor. And so we see this potential difference decreasing, but nowhere near as fast as it did before. Then on the next half cycle, positive half cycle, the capacitor charges up again, and we see that sort of repeating. So the advantage there you can see is that first of all the output doesn't drop to 0, and secondly the output is a little bit more constant than what it was before. There's a little bit of a ripple there, I suppose, sort of a difference between the highest and the lowest, but it's much more constant than what it was previously. The size of the capacitor can be taken into consideration there to make it as small a ripple as possible. So that's the how the half-wave rectifier works. We're now going to have a look at a full-wave rectifier, and you can sort of see there half-wave rectifier. It's rectifying half of the the input to allow the output to be DC. In this case we're going to use the full wave, so you can already start to identify what one of the advantages is going to be. Similar sort of thing, we'll start out with our transformer. This time though, instead of it just being a single diode, it's going to be what's called a diode bridge. A little bit tricky to get the hang of how to draw these. In the end, it's not so much about memorizing the connections, it's making sure that you can think through what's going to happen with the rectifying bridge. So what I'm drawing here is the diode bridge. You can see that it consists of a number of diodes. In fact, it requires 4. Easy way to think of it is that the opposite sides, so if you look at this diode and this one here, you can see that they're sort of aligned the same way, and then the opposite too. The connections then are as follows. We would have our output resistor connected there. That's also going to be connected to the opposite side of the diode bridge, and then from our input we're going to go to the top of the diode bridge and then to the bottom. Now remember that this is not actually a connection here. If those two wires were connected, we'd do a dot there, so those wires aren't actually connected. Now the input again is going to look as it did before. We're going to see that the input is going to be alternating, and the output, we'll need to spend just a second having a good close look at this one. So if we consider positive and negative, we can identify which direction the current is going to flow. So current would be flowing through this way initially. Now when the current flows down to this point, we're going to see that this diode on the left hand side here is going to be reverse biased, and so current will have to flow down the right hand diode. Will then go down through the resistor and come back up this way and gets to this point here. Now because this one was already reverse biased, we know that current can't now flow up, because then it'd be coming back up to this point, and that would then not, just doesn't work. We don't have a decrease in potential across that diode, and so current then has to flow down this diode and then back around to the supply. So that's on the positive half cycle, so this half cycle of the input. If we then have a look at what happens on the negative, and I'll just change colour here to make it a little bit easier to see. On the negative half cycle, that means we're going to have negative at the top, positive at the bottom. So current's now going to flow this way into the circuit. You can see now that this left hand diode is again reverse biased, and so current has to flow up the right hand diode. That then means it's going to flow down through the resistor and flow back up here. And now that we've got this left hand diode was reverse biased, so this one's going to be forward biased, so current flows up through there, around through the top, and then back down. So that means that on both half cycles we have current flowing down through the resistor. So the output potential now is going to look a little bit different to what it did for a half-wave rectifier. So on the positive half cycle we're going to see the voltage across the output across the resistor increase and decrease. On the negative half cycle we're likewise going to see it increase and decrease. So we always have a positive potential across that resistor. So the negative half cycle is being clipped off, and we no longer have any negative on the output, and we also don't have a 0 on the output. So the advantages here, a couple of things to think about with advantages are things like that it uses the whole cycle. So it uses the whole of the input cycle, and again the output is DC, so it's exactly what we wanted to get from this circuit. Disadvantages though, a couple of things to do with disadvantages. Again we have the issue that it's not a constant output. So we could again use a capacitor to improve the output of a four-wave rectifier. And the other disadvantage is that it now uses 4 components, or 4 diodes. That might not seem like a big issue, but if you've got if you're having to manufacture these en masse, if you've got 4 diodes needed each time compared to 1, that's going to significantly increase the cost of producing all of these components. So you can see there a good way of turning an AC into a DC, but still would require some other input. So let's say we that idea of using a capacitor again. In this case, because the cycle is much faster, so it's coming back up again in those negative half cycles, you can see there that the ripple is going to be much smaller as a result. So that finishes off the rectification. We'll finish up this subtopic just by looking at a few other bridge type circuits, not so much related to AC as such, but uses this idea of this bridge of 4 components in order to figure out other quantities.